also it weighs principal superposition. Okay, if I have a system of charges, say in this case here, Q1, Q2, all the way to Qn, then the sum of the forces on Q0, right? I differentiate this the index into Q0 and then 1 to n, what I'll do later on. The sum total of the force is just the sum of the individual forces, okay? And the individual forces is given by, of course, Coulomb's law, Fi is just 1 over 4 pi epsilon naught Qi Q0 over r squared, the direction of r, right? So this is what I have. Then you sum over all the individual charges, okay? And r here, it is, I'm just going to be very relaxed about the notation. R is just the vector from Qi to Q1, okay? And whenever you see a caret, this is the notation that I've been using. I think it's also the notation for cell, okay? Is the not direction, okay? Is this all clear? Now, since the electron is so small, and most charges, elementary charges are so small, and there are so many of them, you can always generalize to a Judge distribution, right? So if I have a body of charges distributed in space, right, and if I want to find the force on a particular charge Q0, how do I do that, right? So what I do is, I find the coordinate system, because the zero of the coordinate is here. Okay. So inside this volume of charges, I take a differential element, differential volume, dx, dy, dz, right? It's just dv prime. Okay? Prime will denote all the charges in this volume here. Okay? And it has a charge density given by rho. Okay? So rho has a unit of Coulomb per meter cube, right? This charge distribution can vary for space. Okay? And each volume element here, each differential volume element here contributes a differential force on Q0, right? And that's given by Coulomb's law, right? Okay, so dF is just 1 over 4 pi epsilon naught, which is the constant, times the density. Oh, I forgot something here, right? It's just the density times dV prime. Right? The charge density times dV prime is just the total charge inside this differential volume, okay? Times Q0 divided by the distance squared, right? In the direction, in the direction of that vector, right? This only denotes direction, and that vector, the distance between Q0 to this differential element is given by this is vector r. R goes from the origin to Q0, okay? And if you do the math right, if you do your geometry right, then this vector here is r minus r prime. Okay? So that's your differential force coming from this differential volume. And because of the beauty of this is because of the principle of superposition, then you're allowed to integrate. You're allowed to integrate. Okay? So the total force F total then is equal to just an integral of F. So I go to there, then it becomes an integral over the whole volume of that distribution times 1 over 4 pi epsilon naught. Usually you put it outside of the integral, in space. And it's just rho prime, rho r prime, Q naught over r minus r prime squared in that direction of r minus r prime. Okay? times dv prime. And dv prime here is just dx. That's the total force, and in general, this is a very difficult problem to solve, right? I mean, people spend a long time if you do mathematical physics, or if you take higher level ENM classes, you do a lot of this, what's called the multiple expansion, and we don't want to do that, right? It's not really what we do in this class. But let's look at an example. Suppose I have a uniform sphere of charge. So this is a sphere. Let me destroy it this way. Okay. And it has a uniform distribution rho. The sphere has a radius a. Okay. And then the total charge is q. Right? So in this case here, rho is just, because it's uniform distribution, rho is just q over 4 pi over 3 aq. Right? And this is the volume. Okay? Now I want to find the force on a particle on a charge q naught at distance r away from the origin. I define the origin now to be at the center of the sphere. Okay, this is the origin. I mean, even solving this is not that easy, right? It's an exercise in doing integration in spherical coordinate, and we won't do that. This is not in lecture, maybe we can do it in discussion. But you know the solution of this problem, right? You can just draw an analogy with gravity. You know gravity, right? Or this is in 7a, right? Because gravity has a similar structure for the force, right? It's central field. And it's also, in this case, it's mostly just because it's central field. And it's also 1 over r squared. Then the force on q naught, so there's all this df, right? So different part of the sphere contribute differently. And then at the end of the day, you have a force on it, and the force is as though all these, this is a lesson from gravity, right? The force is as though all the charges actually is concentrated at the origin. Right? You guys remember this from 7a? And we'll solve this eventually in a much easier way, but when Newton did this, he had to invent calculus, right? To solve this, Newton, in around 1650, he has to calculus. And when he did that, he showed that the total force, at least for gravity, is as though that all the charges here, or all the masses, is at the center. So in this case here, for the case of charge, then F Coulomb here, then is equal to 1 over 4 pi epsilon naught times oh, I forgot to write. So here is still charges are concentrated at origin. Right? This is the result of that calculation. So in this case here, it becomes 4 pi over epsilon naught times q, right? And I just put all the q here, all the charges here at the origin, right? Times q naught, which is the charge of the small little particle here, divided by r squared. right? Where R squared is just the distance of particle Q naught from the origin, right? And in that direction. Okay. And if you want, we'll solve this at discussion, basically going through what Newton did many years ago. Okay, is this clear so far? So now, if I have a system of charges, in particular, I have two charges, Q1, Q0, right? It takes energy to bring these two charges together, right? Because if you want to, because they repel, suppose Q1 and Q0 are positive, right? And they repel one another. So you bring these two charges from infinity into a distance r from one another, right? You have to do work. Right? And that work is an integral from infinity to position r, right? And it's F Coulomb, right? And you have to work against the Coulomb force, so it's the negative sign. Okay? And I'm not going to do this integral, but when you do the integral correctly, you'll find that this is going to be equal to, the work done is going to be equal to, in this case here, 1/4 pi epsilon naught, Q1, Q0 over R. Okay, this is the work that we do. So John could create this charge on equation. Okay, and this is just equal to the energy. We define this to be the energy of the configuration, right? Energy. Okay. It's clear so far? Okay. And one more point of technicality we'll solve is we'll actually look into this more carefully in chapter 2, is that this integral is path independent. I tried to do this last time, but take a lot of time to do. But you should. But by the way, Purcell is probably better, to learn from than me at the lecture, right? So read the book. If you read the book, then I don't have to go through everything. I don't have time to go through everything. Besides, the book is better. Okay. So this is path independent. Therefore, if I look at this integral, okay, this is an aside for later. This is the energy of the configuration, and if I plot it, it looks like this. This is U, this is R, it goes like this. It goes as 1 over R. If they have positive charges, if Q1 and Q0 are like charges. So they repel, they always try to, look at this energy function, right? Things always want to hold down the energy landscape, so, because they repel, they tend to go down.
So why does it work? Integral negative infinity to R.
Oh, sorry.
Why did that?
It's just infinity. Okay? Yeah, there is no negative here because this is polar coordinate. Okay? You guys are familiar with polar coordinate, right?
Yeah.
From physics, from math 53, 54, okay? And if they are unlike charges, then they go like this. Because they attract, right? Active. This is Okay? Now what do you do when you have a system of charges? System of charges, say, 1, 2, 3, qi, n, right? Okay. Now, because of principle of superposition, then the total work done, right? The total work done to assemble all this, right, is the sum of the work done to assemble 1, 2, plus 1, 3, plus 1, 4, and so on, right? Plus 2, 3, 4, and so on, right? Individually, I find the energy to assemble that particular configuration, or just the two of them at once, right? And I sum over all the pair, right? That's the sum over all pair of Wij, right? And W is just in the end, the same as energy here, right? Okay? Yeah. So in this case here, then the total energy is just might as well get used to this notation here. I from 1 to n, j from 1 to n, right? 1 over 4 pi epsilon naught, 2i dj over rij. This is just r by the way, right? It's 1 over r, not 1 over r squared. The force is 1 over r squared, right? But the energy is 1 over r. And then I have to introduce.
So it could be like j equals I to n or something. If you don't.
Yes. But it's easier to just let I go from 1 to n, to go from 1 to n, but I'm not done. But you have the point, right? You have to make sure that sometimes you have to go like this, right? From j is greater than I or something. But this is too confusing, right? It's easy to just sum for I from 1 to n, j also from 1 to n, but then you do double counting in this, right? You count it twice. Right? Because for every 1, 3, you also have 3, 1. Right? So I just have to divide by half or multiply by half. Okay? That's easier. Okay, so this is what this is the energy of setting up this particular configuration of charges. Okay. How about if we have charge distribution? How much energy does it cost to assemble this distribution? Same kind of idea, right? You just have to take that expression for a discrete charges, right? And then just, make an analogy to a continuous distribution. Is this clear? I'm not going to write the formula because I'm not going to use it. But let's. Any question up to here? No? Let's use our understanding of this to actually calculate an energy to build a proton or an electron classically, right? And here is this. So, uniform charge. Say it's charge E. Let's say it's a positron, right? Here's RE. charge E is uniform in this whole sphere. There is a density which is equal to E divided by 4 pi over 3 RE cubed, right? We want to calculate how much energy, how much work, or how much work that you need to do in order to build this charge, right? And don't ask questions why they still keep it, right? Eventually, if you think about this, right, electron will just fall apart because every different portion of the electron, if they have the same charges, right, they will repel from one another. Right? I don't have a quick answer to that, but let's suppose that stay put, right? How much is the energy that it takes in order to build something like that?
Just asking, like, at that level, can anything smaller than an electron actually fundamentally carry a charge? Electron or positron?
Well, we know that they carry a charge, so I guess I'm confused by your question.
Just like when you consider the fundamental, the individual like parts of the electron.
Yes. I mean, that becomes a very difficult theoretical question, right? Does the electron have parts? Right. And it's an issue, quantum mechanical issue, right? And an issue that got solved partially with quantum electrodynamics. That's the future. But even classically, you'll see that there will be problems, as you'll see when we solve this problem. So how do we do this? The way I'm going to do this is I'm going to build this electron differentially, part by part, right? So suppose I already have so this is the density, right? Suppose I already have a sphere or ball of a partial ball of electron of radius r. Right? Let me draw it bigger. Okay. Now I want to ask this question. How much energy does it take to bring dq, right? A sphere dq from infinity all the way to the surface of dr. Okay? So, how do we do that? We know that we know from eventually we'll know from Gauss law, but hopefully I'll get to Gauss law at the end of the class. But right now we just have to draw an analogy with Newton, right? That when you have something like this, then the force is completely equivalent to this. So you have something charged in the center here, and dq over here at distance r, right? Right? And we know that the force here is just 1 over 4 pi epsilon naught. Okay. The total charge in this sphere, what is the total charge here? The total charge here, Q as a function of R is just rho times the density times the volume, right? 4 pi over 3 R cubed. Okay. So the force at that point, the F is just rho 4 pi over 3 R cubed, okay, times Q naught, okay, no, times dq, sorry, right, because this is a small differential charge, times dq over R squared, right, okay, in the direction of R, okay. Therefore, the energy to bring this all the way from infinity to that position R, right? The total energy, let me write it somewhere else, but let me just write it here. U is just from knowing this, right? To U then is just 1 over 4 pi epsilon naught, okay? Rho 4/3 pi R cubed dq over R. Okay? So this is how I assembled it. I add a little bit of dq at a time, and then I have the whole sphere. Okay? So how do I do that? Now first, I can just put this dq anywhere, right? This dq can be anywhere along the surface of the sphere R, right? It doesn't matter, it has the same energy, right? It only goes as 1 over R, right? So, in theory, or in practice, when I actually do this integral, I'm going to bring a spherical shell of thickness dr, right? So this is R, radius R with a thickness dr, right? And I bring this over and I just put it on top of the sphere, right? Okay. And how much charge do I have in here? dq, then it's just rho times the volume of this sphere, right? The volume of this shell, right? And the volume of that shell is 4 pi r squared. Okay. Oops. Okay. So substituting dq into this equation, I get du. So when I do that, right, instead of this, I have something like this. R, right? And du is just 1 over 4 pi epsilon naught rho, just doing this equation here, rho 4/3 pi r cubed times dq, but dq is just rho 4 pi r squared dr, the whole thing divided by r. Okay. Now, some of you might ask, well, do I have to worry about the energy to assemble the shell? Right? Remind yourself to ask me this question after we solve this problem. Okay? That's an aside for now, but suppose we can ignore that, then to find the total energy, all I need to do is integrate from 0 to RE, which is the radius of the positron. Right? The reason I'm using positron is because I don't have to worry about negative number. Right? Positron has positive charges. So 0 to RE, right, of U. Okay? So this becomes, so some of the 4 pi cancel, I have this 4 pi cancel that 4 pi, right? So I have, is that correct? I better look at how many it is. So the 4 pi cancel, then I have rho over 3 epsilon naught, right? Times an integral. So you have r fifth, right? This is there's another 4 pi here. Is that right? Is that another 4 pi? Mm-hmm. Right, there's another 4 pi, and then you have r to the power of fifth, and you put the 4 pi outside. Right? R to the power of fifth times 2. 0 to pi.
The R should power go over here.
Sorry?
Because you're not in the denominator.
Yes, this is in the numerator.
Right, the one
4 pi in the numerator.
No, because it's R cubed times R squared over R, so should
Oh, rho squared.
yeah.
Right, and I have r cubed, r squared divided by r.
So that's r to the fourth. Right?
Oh, sorry, f to the fourth. Right, okay. So when you do this integral, what do you get? You get 4 pi rho squared over 3 epsilon naught, 1/5 of RE to the power of 5, right? Right? This is why we mistake, because R to the power of 5 over here. That's the total energy, right? So let's express this energy in terms of the total charge of the electron, or the positron. Then, since rho is equal to E, which is the charge of the, if E is positive, then it's the charge of the positron. Unless you guys don't know this, the positron is just the anti of the electron. Same mass has a positive charge over 4 pi over 3 RE to the power of 3, right? So I substitute this density into this equation, then I would get, if you do it right, I would get 3/5. Do you want me to do this? No, right? But basically you substitute that equation into the whole square. Right? And you'll get this, just remember at some point, this square. Right? So this is the energy it takes if you have to assemble the electron and the positron from scratch, from far away at infinity, differentially until it becomes a uniform sphere of radius RE with a total charge E. Right? As you see, it doesn't really matter whether it's electron or positron because it's E squared. Okay? So that's the answer. Yes.
I mean, can you say that?
Oh. Let's just do it then. Can we just do it, right? So if I U is 4 pi, then rho is E over 4 pi
Oh, you said
over 3 RE cubed squared, right? Over 3 epsilon naught, right? And then you have 1/5 RE to the power of 5, right? So you have RE to the power of 5, then you have RE to the power of 6 here.
Yeah.
That's why you have 1 over RE in the numerator.
Right.
Right? Okay. Is this clear so far? Okay. Question? Notice what happened, right? That if you assume that an electron has 0 dimension, right? If RE goes to 0, then the energy goes up. Right? This is the problem. This is the problem for classical electrodynamics. Right? If an electron is a point charge, then the energy goes up. Right? But if the electron has a finite radius, right? If RE is finite, right? Then what happens? Of course, U is finite. But if an electron is finite, then this is what you do, right? This is how you construct it, right? Then it will also fly apart, right? It's not stable, right? Because the energy goes positive, right? The energy goes 1 over R. It will just, because of each different portion repel one another, it will just fly apart. That's the problem. And if you continue on in physics, you'll try to find partial solution in quantum mechanics or quantum electrodynamics. Any questions so far? Okay. Now, what is the radius of electron? So, now you remember from relativity, because you haven't done relativity, right? But this is in t-shirts everywhere, right? Energy is
MC squared.
right? And suppose all the energy let's pretend, or suppose. The reason I say pretend is because this thing is just still molecule, right? Suppose all the energy comes from electrical energy. Okay. Then what you have is E equal mc squared, right, is equal to 3/5, 1 over 4 pi epsilon naught, E squared over I. Okay. And if you plug in the number, right, I never know this number, but in chapter 2 we'll talk about potential. This is actually 1/2 MeV. Right? And then you'll find that RE is about, anybody have a guess? It's called the classical radius of electron. Sometimes it's called the Lorentz radius. Sometimes it's called the Thomson scattering radius. Question? No? Okay. Let's move on. To a little bit of bookkeeping, right? Remember when you have a system of charges, I already erased that. When I have a system of charges, I have, just look at that drawing. The total F is 1 over 4 pi epsilon naught, sum over I from 1 to n, right? Qi over Ri squared in the direction of Ri, which is Q naught, right? Okay. Just like Q1, Qi, Qn. Okay, and there's a total force. Okay, now if I divide, this is just a matter of bookkeeping, right? It's bookkeeping. Then let me bring this Q naught to the since Q naught is constant, let me bring it outside. Okay. So let's divide the force by Q naught, okay? Because this is the charge that I have, that I call the test charge. Okay? And what you have is just 1 over 4 pi epsilon naught times I from 1 to n Qi Ri squared in the direction of the R. Okay. Okay, and I define this to be the electric field at this point. Let's call this point B. Right? Electric field at point B. Okay. That's the definition of it. As simple as that, right? Some books goes into the technicality of making sure that Q naught goes to 0, but that's mute. What matters is that this is, for now, just take it as bookkeeping. So the force on Q naught then is just Q naught times that electric field, right? At P. So you have a system of charges, right? I can calculate the electric field. Once I calculate the electric field, if I put a charge Q naught, then the force on that charge is just Q naught times the electric field. It's as simple as that. Okay? And mathematically, this is completely just bookkeeping. Right? And we're ignoring the fact that the Q naught itself can produce its own electric field. Right? But this is problem that are similar to problem of this. Right? So I'm going to ignore that.